next session with Sandeep PAWAR, who's joining us from Greater Chicago. Hi, Sandeep.
Hi.
And, thanks for joining us today on this wonderful boot camp. And so Sandeep is going to talk about model interpretability. All right. So we all, most of the times we worry about the model accuracy, but no one, gives a lot of thought of our model explainability or interpretability. For which Sandeep is going to, enlighten us upon this point how important it could be for making strategic business decisions. And Sandeep is seasoned, data scientist and has been working in analytics for quite some time. So Sandeep, the stage is all yours. Please, we look forward to your talk.
Okay. Thank you so much, Priyanka. Really appreciate it. Setu as well, and all the other organizers for giving me the opportunity. I'm really looking forward to joining the rest of the sessions as well. It's a really good lineup, and I'm pretty excited about it. So, as Priyanka mentioned, I won't go over the same details again, but I'm a simulation and data analytics engineer at Lighting, US. My background is actually in mechanical engineering, but I have been doing statistics and data analytics for the past 4 years in my company, combining both my manufacturing product development experience with data analytics. Primarily use the Microsoft data analytics stack, so Azure ML, Power BI, Python for the most part. I'm very active on Twitter, so you can join me there, connect with me there at PAWAR BI, and I also write blogs at powerbi.com. Feel free to connect with me on LinkedIn as well. And just a quick reminder, I have another session scheduled tomorrow on time series forecasting in Power BI. So before I discuss the agenda for my topic today, I want to set the stage first. Let's consider a typical machine learning process. We start with some data. For the purposes of this presentation, we're only going to consider tabular data to simplify things. Perform the EDA, clean the data, get it ready, and then create our feature pipeline, feature transformation pipeline, and then feed it into the model. Very typical process. We usually start with some baseline model, something like linear regression or logistic regression if you're working on classification. We define some accuracy metric, we define some business evaluation metric, and then make the predictions. Usually, these linear models aren't flexible enough. So what do? We've learned from all the Kaggle competitions and all the papers and then all the cool notebooks that we have seen. We progressively go from these linear models to more tree-based models like random forest and then gradient boosting models. Everybody's favorite XGBoost, you have to try that. And then you keep going and chase that accuracy. So you want to extract that accuracy as much as possible, every single percent of it. And you create these complex multi-stack ensembles to get that accuracy. But do we really create an accurate model? We chase this mirage of accuracy, but the question really here is, do we really create a model that is accurate? And this accuracy fallacy that I call it, that I'll explain that in a bit. So creating these models is not new. So what you're seeing on the screen on the left-hand side is the Copernicus model and a Ptolemy model. So Copernicus and Ptolemy, they both were astronomers in the 1400s. And what they did was Ptolemy created this geocentric model of the solar system, which he said Earth is at the center of our solar system. Copernicus, many years later, said that sun is at the center of the our solar system. Now, interestingly, both of them created these models and then predicted the movement of all these celestial objects or planets around that are around us, and both were very accurate. Now, I don't have to tell you obviously which one of these two models are correct. Obviously, the Copernicus model, we know that the sun is at the center of our solar system, but did they create accurate model? If you consider the accuracy metric based on traditional methods, then yes, Ptolemy was accurate, but was it the correct model? Probably not. In fact, most definitely not. So the point I'm trying to make here is we chase this accuracy as much to really great extent, but that does not necessarily guarantee that we are creating correct model. Another fallacy that we often see with when we are creating these models is we chase after these highly complex models because of the bias and variance trade-off. That if you when we start with the linear models, those are high bias models and they don't create accurate predictions. But when you create these complex models, which are the high variance models, they are not generalizable at all. And in that process, we think that by creating these complex models, we are getting more accurate results, which is not true. And then I'll show you that with example. But the consequence of that is when we are chasing this, when we are creating these highly complex models, the interpretability of these models suffers significantly. So highly complex models are likely to be less interpretable, but not necessarily more accurate. So in 2018, there was this competition by FICO. So FICO is a financial, I think, company here in the US, maybe globally as well. But they had an explainable machine learning challenge, and what they did was they provided a data set, a tabular data set, and they asked the participants to create these black box, very highly complex machine learning models. And at the end of the competition, what they found was there was no performance difference between the interpretable models, meaning less complex models, and these highly complex models. So overall, in tabular data sets, study after study, for tabular data sets, study after study, it's been shown that when you create these complex models, you think you are creating accurate models and making accurate predictions just based on single accuracy metric, but you are not. And we think when we create these models that we are making them interpretable. I haven't defined interpretability yet, but one of the steps when we create these models is we create feature importance plot. So we look at, so for example, if we are creating a random forest model or XGBoost model, both of those, they allow you to compute the feature importance. But feature importance tells you that globally, on an average, as an aggregate, which features contributed to making the predictions. What they don't tell you is that how those features made the predictions at the global level as well as at the individual level. So interpretability, it answers the question, how do the features make the predictions? Not what features make the predictions, but how those features make the predictions. I hope that's clear from the examples. Interpretable models are also constrained, so monotonicity is very important, and they are domain specific. Because if you want to be able to, interpret these machine learning models, you need to have domain knowledge. If you don't have it, you need to collaborate with somebody who has the domain specific knowledge. Why do we need interpretable models? Because they are easy to understand and troubleshoot. Again, I'll show you that in my demo, that how it leads to some counterintuitive explanations about the model. It also lets us debate the fairness, if the model is fair or not. If you are deploying these models in commercial applications where decisions are being made about whether to give somebody a loan or not, or to arrest somebody, or a lot of other scenarios where protected classes may be at risk. If you do not create these interpretable models, then there is no way for you to look into them and identify what's wrong. So creating these interpretable models at least.
Hey guys, just a bit problem. Hey guys, still trying to get Sandeep back. Just stay put.